All right. Good morning, everybody. Welcome back. This week, we will continue talking about um, molecular equations and overall ionic equations, as well net ionic equations. And then we will advance to talk about electrolytes and then cover concentration. And hopefully we can start talking a little bit about oxidation number. Okay, so let's start here with some important announcements. Let me share my screen with you. Okay, so for this week, we will have in-class assignment this coming Friday. Okay, so don't forget about that. And you also have online homework for chapter number 4, part 1, due on Thursday. Okay, don't leave for the last minute. Okay, so what we are discussing here is acid-base reactions. Acid-base reactions are always a double displacement reaction, and the products are going to be a salt and water. The salt that is formed during the reaction may be a soluble salt. In this case, in solution, we are going to find the ions, or maybe an insoluble salt. And in this case, if the salt is insoluble, we will not find ions, but the compound as a unit, and the physical state will be a solid. When do you know when a salt is soluble or when a salt is insoluble? You have to refer back to the solubility table. Okay, always look at the solubility table. And to determine the solubility of any salt, you just need to use the cation or the anion. Whatever is present here in the solubility table, that's enough to figure out the solubility of the salt. For example, salts formed by the group 1, containing ions from the group 1, they are soluble and there are no exceptions. When we move on to, for example, salts formed by carbonate, they usually are insoluble, and the exceptions are salts formed with cations from group 1 and ammonia. Okay, so that's how you are going to use the solubility table to determine the solubility of the salt. Let me just go back here. Okay, and remember, we can write the acid-base reaction in 3 different ways. First one is the molecular equation that will consider just the molecular form of the compounds. Overall ionic equation, where we are going to consider all the ions that are involved in the reaction. And then if we have any kind of spectator ions, we may cancel them and they will not show up in the net ionic equation. Okay, so I always like to start with the molecular equation, then move on to overall ionic equation, and then the last one would be the net ionic equation. So we did some examples last week. And now what we are going to do is take a look here at some reactions between 2 salts. Okay, So usually the reaction between two salts are going to yield one salt that is insoluble and another salt that is soluble. And here the same thing. I'm going to always start with the molecular equation, considering the compounds in the molecular formula, and then we will move on to the overall ionic equation and net ionic equation. So our first example here, we are going to deal with lead nitrate and sodium iodide. Okay, so just give me hopefully here a couple minutes because my iPad is updating. So if doesn't finish to update, then I will open a PDF here. Okay, so just give me a couple minutes, please. Okay, so I think this will take a little longer. So what I'm going to do here is to open the PDF, and once the update is completed, then we can move on to the other screen. Okay, sorry about that. Okay, so we are going to deal here now with the reaction between two salts. So first thing that we must know is how to write the formula of the salt. So let's start with lead to nitrate. So we know that nitrate is NO3 and the charge is 1 minus. And here our cation is a transition metal, and in this case, lead between parentheses 2. Okay, so when we have this kind of nomenclature, what this number between parentheses telling us is the charge of the cation. Okay, so therefore we have here lead in the 2 plus state. Because this is an ionic compound, remember we have a cation and an anion, we have to cross the charges. Therefore, lead to nitrate is PbNO3 2. So that's going to be the first salt in the reaction. Okay. Okay, so I have my screen back here. So let me switch to the iPad. Okay, so that's what we have figured out so far is the formula of lead nitrate. Again, lead, Pb. The number 2 here indicates that this is a 2 plus cation. Nitrate is always 1 minus. Cross the charges, therefore we have PbNO3 2. And this salt is going to react with sodium iodide. Iodide is I minus. Sodium belongs to the group number 1, therefore it's 1 plus. Okay. Therefore, we don't need to cross any charges because they are 1 and 1. So we have here sodium iodide. The reaction between two salts is also a double displacement reaction. That means the positive cation from one salt is going to combine with the negative part from the second salt, and that's going to produce PbI. Remember that we are dealing with lead in the 2 plus state, and iodide is always 1 minus. Crossing the charges, we have PbI2. Because it's a double displacement, the positive part from the second salt is going to attract the negative part from the first salt. And as the result, that's going to form NaNO3. NO3 is 1 minus, sodium is 1 plus, no need to cross any charges. Okay, so now the next step in the molecular equation is to determine if we have any solids being formed during the reaction. So we have two options here, lead iodide and sodium nitrate. Let's refer back to the solubility table. So let's analyze first lead iodide. So let's go back here. So we may look for lead or iodide. Whatever we find in the solubility table is enough for us to classify this salt as soluble or insoluble. Here, if you look at the fourth row in the solubility table, we have here chloride, bromide, and iodide salts. They are soluble. The exceptions are when they are combined with silver, lead, or mercury, that will yield an insoluble salt. And in the present case, we have iodide bonded to lead. Therefore, this first salt here is insoluble. And the way to indicate that is placing the physical state as a solid. The second salt, sodium nitrate, that's formed by an ion from group 1, and that will always yield soluble salts. Okay, so therefore sodium nitrate stays in solution. And in fact, when we mix lead nitrate and sodium iodide, we will form immediately a bright yellow precipitate, as shown here in the figure on the right side. And the identity of this precipitate is PbI2. Okay, So this here is a precipitate, and the color of this precipitate is yellow. So therefore, usually when we have lead in solution, one way to separate lead from the solution is by adding iodide salts, okay, that will cause the precipitation of lead. We can filter off the solution and isolate lead. Okay, so now the next step is to write the overall ionic, oh, sorry. Before moving to the overall ionic equation, we must balance the molecular equation. We have two iodides in the right here in the product side. So therefore, we need two on the reagent side. As a result, now we have two sodiums, then we need two sodiums here, and then one and one, and the reaction is balanced out. Okay, so now let's move on to the overall ionic equation. The secret here for the overall ionic equation is to pre-react the reagents with water, and that will cause the formation of ions if the salt is soluble. So let's start here with lead to nitrate. If this salt is soluble in water, we are going to split the cation and the anion. So go back to the table. Nitrate salts right here in the third row, they are soluble and there are no exceptions. Therefore, every time we have lead nitrate in solution, we actually have lead 2 plus. Because is in solution, it's aqueous, and nitrate 1 minus in solution as well. Attention here, we have two nitrates in the structure. Therefore, we have to produce two nitrates in solution. Same thing for sodium iodide. Sodium iodide is a salt formed by a group 1 cation. Therefore, they are always going to be soluble. So we have here sodium plus and iodide 1 minus in solution. So one thing that I like to do here, and will avoid balancing out the reaction later, is to use the same stoichiometric coefficient that was used in the molecular equation, okay? So we know that we need to have two sodium iodides to react with each lead nitrate, and then you just inherit the stoichiometric coefficients here in your equation. Okay, so now we do basically the same thing we did before. The positive ion from one salt is going to attract the negative ion from the other salt. Lead 2 plus will attract iodide, and we know that this will form a insoluble salt. Therefore, in solution, they are not split. They are found as one unit. And the identity of this salt is lead 2 iodide. And the positive part from the second salt will attract the negative part from the first salt. Always place the cation first, followed by the anion. Oops, sorry. Okay, so in the case of sodium nitrate, this is a soluble salt. Therefore, they are not going to be found combined in solution, but as free ions. Okay, so because sodium nitrate is soluble, they are going to be found in aqueous solution as Na plus and nitrate minus. And we know here that we have two sodiums and two nitrates, and we just balance out. Okay, so now from the overall ionic equation, it's very simple to obtain the net ionic equation. So we are just going to cancel out whatever ions are present at the beginning and at the end in the identical form. And remember, every time we have the same ions or ion before and after, those are called spectator ions. So let me rewrite the overall ionic equation here. And that's going to keep a little bit cleaner. Okay, so there we go. Let's see what we can cancel and what we cannot. So just looking here at first sight, we see that we have two nitrates before and the two nitrates after. Therefore, we may cancel them out for the net ionic equation. And the same thing with sodium. Two sodium plus before and two sodium plus after. Therefore, they can be canceled. Okay, so sodium and nitrate in this reaction, they are just looking at things to happen. They do not form anything new. I cannot cancel lead 2 plus because on the other side, we have lead combined with iodide. Therefore, it's not the same thing, which means it cannot be canceled. What is left here is lead 2 plus AQ reacting with two iodides, AQ as well, will form PbI2, and that is a solid. Okay, so that's the net ionic equation. And that's how you are going to write the reaction between two solids. Okay, very good. So let me just make an observation here regarding acids before we move on. Okay. So in the last example, on Friday, we dealt with H3PO4. Some books, when you have H3PO4 or any acid that has more than one hydrogen in the formula, they will not lose the three hydrogens at once. Okay, so you might find the stepwise reactions. Okay, so lose one hydrogen first, then the second, then the third. Here, just to make things more convenient, every time we have more than one hydrogen, we will consider that we are going to lose all the hydrogens at once. Okay, so that's the way we will deal with acids that have more than one hydrogen that can be ionized. So this will just make things easier and avoid dealing with this kind of anions in the equation. Okay, very good. So now that we can write equations between acids and bases and salts, so let me go back to the PowerPoint and let's talk about ions in solution. Let me share our PowerPoint screen. Oh, and then just one thing before we move on. So just know that precipitation is an efficient way to quantify a determined ion in solution or remove an undesirable contaminant from the environment. Okay. For example, calcium 2 plus may be found in water. And one way to remove calcium 2 plus from the water is by adding aluminum sulfate or soda ash, which is sodium carbonate. Okay, so when we add aluminum sulfate, calcium is going to combine with the sulfate, and that will produce calcium sulfate, which is insoluble. And this way we can filter the water out and eliminate the calcium 2 plus from the water. And the same principle when you have sodium carbonate. Okay, this calcium 2 plus will combine with carbonate and release sodium plus and form calcium carbonate, which is insoluble as well, and this can be filtered out. Okay, so that's the process that's used in water purification to remove calcium 2 plus ions, for example. Okay, so let's talk about electrolytes and non-electrolytes. Electrolytes and non-electrolytes is just a formality. We kind of already know what is an electrolyte and a non-electrolyte. So let's just be more formal here. Solutions are classified according to their ability to conduct electricity in electrolytes and non-electrolytes. Electrolytes conduct electricity and are subdivided into strong electrolytes, which are excellent conductors, and weak electrolytes, which are average conductors. And non-electrolytes, they do not conduct electricity. A very simple test that we can perform to classify any solution as electrolyte or non-electrolyte is to have a solution of the compound, two plates immersed in the solution. Then here we have a source of electrons, and we will complete the circuit with a lamp. For the lamp to emit light, we need the charge to flow from negative to the positive pole and create here an electric current. If the solution is a non-electrolyte, there will be no light in the lamp. If the solution is a very strong electrolyte, we will have a bright light coming out from the lamp. And if it is a weak electrolyte, then it will not be so bright. Okay, so by the brightness of the lamp, we can determine the amount of electrolytes in solution and thus classify as strong electrolyte or weak electrolyte. And remember, electric current is simply defined as the movement of charges. Compounds that allow the movement of charges are called conductors. For example, metallic solids as, for example, copper, they allow the movement of charges, therefore they are conductors. And any solutions that have free ions are also going to be electric conductors.
Excuse me, George.
Yes.
What was the other compound on the precipitation, the precipitate slide, excuse me? It was aluminum 2 SO4 3, or
Let's
I didn't
go
have
back
time to
here.
write it down.
Sorry about that.
Oh, thank you.
There you go. Let me know when you are ready.
Perfect, thank you.
Okay, no problem. Okay, so I'm not going to spend too much time here with electrolytes and non-electrolytes because this is not the goal at this point. You will have the opportunity to investigate this later on. Okay, what I need you to know here is given any salt in water, to classify if the salt is an electrolyte or non-electrolyte. Okay, so we will not deal here with the case of weak electrolytes. And remember, to be classified as an electrolyte, we must have free ions in solution. And non-electrolytes, they will not form free ions in solution. Okay, so let me give you some examples here, and then I will move on because it's not worth to spend too much time discussing electrolytes. Okay, so let's deal with ionic compounds, because those are the ones that usually form electrolytes in solution. So for example, let's start with sodium nitrate that we saw before. So when I say free ions in solution, I'm talking about, for example, sodium plus and nitrate minus. Okay, so those are considered free ions. They receive the name of free ions because they are not bonded and forming a solid. And on the other hand, for example, what we saw before, lead iodide, we know that this is an insoluble salt. Therefore, we do not have here a free ion. Okay, so therefore, in this case, no free ions, because this is insoluble and this is a soluble salt. Therefore, a salt solution that is an electrolyte is going to be always formed by a soluble salt. And a salt solution that is a non-electrolyte is always going to be formed by an insoluble salt. So for example, here then, when we have nitrate in water, because this salt is soluble, we are going to have in solution the free ions. And therefore, this will be an electrolyte. Okay, to form an electrolyte, we have to split the salt and form the free ions. And as I told you before, lead iodide, that is a solid, and in water, it remains a solid. So see here that the ions are not free, they are bonded to each other. And in this case, we have a non-electrolyte. And again, that experiment with the lamp, you can determine by the brightness of the lamp how strong is the electrolyte, and maybe even build a scale if you want to. Okay, so then I already told you about the electric conductivity of lead iodide in water, because this is an insoluble salt that will not conduct electricity in water as well. Okay, very good. So now we got to a point that I want to spend a little bit more of time, and that will be the last thing I will talk today, because we are running towards the end of the session here. So now let's talk about concentration and dilution. So we know that acids, when they are in water, they will form H plus and the respective anion, and bases, when in water, they will form OH minus ions, which are called hydroxyl ions, and the respective cation. Okay, so in both cases, in water, we have free ions. Some salts, when dissolved in water, they are soluble, therefore they will form also free ions. And on the other hand, some salts are insoluble, which means that the bond between the cation and the anion is so strong that water cannot split them and they will form non-electrolytes, okay? So no free ions in solution. Concentration is just a way to measure the amount of entities in a solution. Those entities may be cations, anions, or even molecular compounds. Okay? The concentration will tell us how many entities we have in a determined volume of solution. So let's compare here the picture that I'm showing you from on the left side and the one on the right side. Okay, so huge agglomeration of people here. Maybe that will take 5 more years to see something similar to that. So that belongs to the past. Okay, so comparing the picture from on the left with the picture on the right side, we can see here that the picture on the left side has more people in the same area than the picture on the right side. Therefore, we can say here that on the left, we have a higher concentration of people compared to the one on the right side. In chemistry, the idea is very similar, but we are dealing now with molecules or ions, okay? So we can calculate the concentration of anything. And concentration is a measurement of the amount of entities in a given solution. The unit of concentration in the international system is mole per liters, okay? So I can represent mole space liters to the -1 or mole slash liters. This unit is also called molar concentration, and it may be represented instead of mole per liter as a uppercase M. Other units that are also used for concentration are kilograms per liter or grams per milliliter. How do you calculate the concentration of any solution? The molar concentration, I'm showing you here the formula on the left side. C stands for concentration. Molar concentration then is going to be the number of moles in a determined volume of the solution. Okay, so again, we can calculate the concentration of any solution. We need to know the number of moles and the volume of the solution. Any solution has two parts. One is called solvent, and whatever is dissolved in the solvent is called solute. So for example, an aqueous solution of sodium chloride, water will be the solvent and sodium chloride is the solute, okay, or whatever is dissolved in the solution. If I'm measuring concentration in mass per volume, then what we are going to use here in the formula is the mass of the solid dissolved in the volume of the solvent. Okay, so again, those formulas here, they will be used to calculate the concentration of any sort of solution. You may have a compound dissolved in water, for example, or the concentration of ions dissolved in water, for example. Don't forget the units, they are very important. If we are talking about molar concentration, the unit is going to be mol per liter, or it is also represented by an uppercase M. If we are talking about mass per volume, then we can use kilograms per liter or grams per milliliter, okay? So the exercise will specify the unit to be used. Okay, and I think with that, that's a good point for us to stop. On Wednesday, we will talk about dilution, and then we will start oxidation states, okay? So I hope you have a good week, and I will see you tomorrow during the discussion section.
Thanks, George. Have a great day.
Bye-bye.
Have a good rest of your day.
Thank you.
Thank you.
Thank you, Professor.